Okay then. Good afternoon once again. So this morning we started the integration chapter, section. Okay, I spoke a bit. I kind of did a look ahead at some of the different kinds of integration that we were going to be seeing coming up. In particular, what I refer to as double integrals over two-dimensional regions of the plane. These are the ones that are most easily seen as extensions or generalizations of the regular one-dimensional integrals you're familiar with, integrals of functions of a single variable. Well, we started off by looking at these line integrals or path integrals. So this is a situation where we've got two variables, x and y, and functions p and q, depending on the two variables, x and y, and where we're integrating this linear differential form, p dx plus q dy, integrating that over a curve C in the plane. Okay, so we did some initial examples of those this morning. And just to look at a further example, before going on to the double integrals, just look at a further example of these in section 1.12, which is where we're looking at integrals along parameterized paths. Okay. So sometimes the path P, or the path C, rather than having a description of it in terms of how x and y are behaving, which is what we saw in the previous examples. Okay, in one example, we were integrating along a curve defined by the equation y equals x squared. In the other examples, we were integrating along straight line segments parallel to the x and y axes. Again, that's very easy to describe in terms of the behavior of x and y. If you're parallel to one of the axes, one of the variables is fixed, and the other one changes. Okay, but sometimes the path will be parameterized by a third variable. And a typical one that's used is the variable t. So C will be specified as the curve with coordinate functions x of t, y of t. So two functions that are giving you the x and y coordinates of points on that curve between some starting and ending values, of the variable t. Okay, so between a t0 and a t1 set. And this will define the curve in the x and y plane. So this will be x of t0, y of t0 will be the starting point, and then you proceed to x of t1, y of t1 as the ending point. And for these kinds of for situations where you have the curve parameterized by a third variable or a parameter t, then it makes sense to convert the given path integral into an integral with respect to the variable t. Okay. So we'll look at example 1.16, which looks at one of these. So here we're talking about the integral I of the linear differential form x squared dy minus yx dx. And our curve C is parameterized for us. So C is a semicircular path, a circle of radius 1 and traversed clockwise from the point minus 1, 0 to 1, 0. So the point minus 1, 0 is this point here. And the point 1, 0 is this point up here. And we're going semicircular path traversed clockwise. So we're going on this semicircular path here. A circle of radius 1, then this is going to be the point 0, 1. So this is our curve C. Okay, well, you You might describe that curve C in terms of the x and y coordinates directly, but then you're going to have, because you're talking about a circle, you're going to probably have expressions to do with the square root of the sum of squares of x squared and y squared. It's the radius term. But if we're pushed in the direction of parameterizing this curve, then that's kind of easily done. Okay, C can be parameterized so basically cosine t sine of t. Okay, so the point on the unit circle will have coordinates cosine t y of t. But if we want to start at this point here and end at this point, then our starting value of t would be in radians minus pi, and the ending value would be 0. So t would proceed from the value of minus pi, which is give us the starting point here, and increase to 0. So this is our x of t and our y of t. And from these functional expressions for x and y, you can derive expressions for the differentials. So dx is going to be the differential of x, but if x is cosine of t, then it's going to have the differential minus times sine of t dt. And similarly, dy, you take the differential of y, you're taking the differential of sine of t. So applying the chain rule here, it's going to be cosine of t dt as well. And so using these substitutions, replacing x and y with cosine and sine of t respectively, and replacing the differentials dy and dx and dy, sorry, this should be dy, second one I worked out there. We can replace all parts of the linear differential form with their equivalent expressions in t. Okay, so the integral becomes x squared, which is cosine squared of t, times dy, which is cosine of t dt. Then we've got minus yx, which is going to be minus the sine of t, cosine of t. That's the minus yx part, but then you're multiplying by dx, which is minus sine of t dt. Now everything is quoted in terms of t. The path C has been encoded into this expression because we've replaced x with cosine of t and y of sine of t. So all we have to worry about is the starting, is the range of values for t. And t is going from a starting value of minus pi to an ending value of 0. And we can work on this expression here because this now looks just like a regular single variable integral. And we can factorize that as cosine of t to cosine squared of t plus sine squared of t.
Killian?
Yes?
In the notes, t goes from pi to 0 as opposed to minus pi.
Yeah, of course, that's right. Well, sorry. Yeah, if I did minus pi to 0, if I did minus pi to 0, I'd be going that way, wouldn't I? Yeah, excuse me. So the curve I'm actually... Because if I'm going... So this one is actually t going from minus pi to 0. So yeah, so I should be changing to... Yeah. So t starting at pi and going to 0. Yeah, thank you for that. but starting at pi and decreasing to 0. That will send me along the upper branch. Yeah, thanks for spotting that. So this upper branch is pi t starting at pi and descending to 0. Okay, but everything else goes through the same. And of course, this is our well-known, recognized radius 1 term, cosine squared plus sine squared. So the integral just becomes the integral from pi up to 0 cosine of t, which is something we recognize. So it has an integral of sine, which happens to evaluate at the two endpoints, both endpoints to 0. So in total we've got 0. Okay, because sine of 0 is 0 and sine of pi is 0 as well. But it demonstrates the way parameterization can be used to evaluate and compute these integrals as well. Now, to get us ready for the tutorials, I'd like to go on to the double integrals and open up exercises 1.6 as well. And it's good to see the second type of integration early on as well. So the picture I drew this morning
Which exercise?
Sorry?
What are we doing? What exercise?
No, we're going on now to section 1.14. I want to open up the next set of exercises as well by doing this material. So going on to page 28 now. Okay, remember, associated to our function of two variables, we have a surface, z equals f of x, y. This is what we were drawing this morning. We might have a region in the plane, R. So R is a subset of the domain of the function. Remember, just as an interval a to b was the subset of the domain of a function of a single variable, y equals f of x. And there the integral was the area between that region of the domain and the graph of the function and the area between these two. When we're in the basic function depending on two variables, we're talking about the volume of the cylindrical region with the region R as its base, the projection of R up onto the surface as its top part, and it's got these vertical walls parallel to the z-axis. Okay, so what we want to capture here is the volume of this cylindrical region. I'll put cylindrical in quotes. Now, the question is, how can we get at the volume of this region? Okay. We'll write this as this kind of integral, which for the moment is really just a bunch of symbols for us at the moment. I haven't given a mathematical meaning to it yet. Okay. But what I will do now is give a mathematical meaning to this bunch of symbols in such a way that we can appreciate how it does give the volume, of this part of R3. Okay. This dx, dy, this is known, just some terminology for later, this is known as an area element of the xy plane. Dx, dy. You can think of it, for the moment anyway, you can think of it as representing the area of a small rectangular region, where there's a variation dx in the x direction and a variation dy in the y direction. And it's talking about the area of this. So the volume of the cylinder above can be approximated if we split. Okay, a lot of chatter there. If we split the region R, or subdivide the region R into many small rectangles. Here's our R. We can imagine lots of vertical lines parallel to the y-axis, and lots of horizontal lines parallel to the x-axis. Subdividing this into many small rectangles Ri. So R we can regard as the union, or as approximately the union over I of the small rectangles Ri. I say approximately because something funny happens at the edges where maybe the rectangles leave bits of R unaccounted for, or maybe the rectangles creep outside the boundary of R. The boundary of R is curved. There's a little question about what happens at the boundary. But we'll disregard that for the moment. And how can we estimate this volume of this region here by making use of this subdivision? Well, the volume line over a small rectangle Ri will be approximately the area of Ri multiplied by the value of f at xi, yi, where xi, yi, now you could take it as the center point of each of these rectangles. We don't really need that. We just need where xi is some point in Ri. So if I take the area of Ri and multiply it by the height, the value f of I xi will be a height of a portion of the surface that lies above the little rectangle Ri. So that gives you one kind of slender, thin piece of the whole volume that we're trying to get at the size of. So if I add all of these up over I, I'm a bit vague about the limits of I, but I is just indexing all these small rectangles. Okay, so there's loads of possible values of I, and it's just locating or indexing each of these small rectangles. Well, if I add all these volumes up, this is an area of the base times the height of this little part of the volume lying over the small rectangle Ri. If I add all these volumes up, I'll get an approximation to the volume of the region I'm trying to describe. So this will be approximately the volume of the region described above. The region of R3 between the region R in the xy plane on the one hand and the volume of the surface on the other hand, on the top part and with the straight vertical walls. Okay, it's the approximation, okay, the reason it's not exactly the same is because around each rectangle here, I'm just choosing, it's got some image up here, I'm just choosing a single point to represent the height of it. I'm using that as the height of my tall little cylindrical piece, okay? So to represent, see this thing really it may have some kind of a curvy top or slanted top because the surface might be undulating over this. But I'm just using a single point to represent the height of it. So bits of this tall, thin box or cylinder with the base of one of these small rectangles, bits of it at the top might poke out above the surface or might be underneath the surface, depending on how the surface is undulating. Okay? Because to represent the height of this thing, I'm just using a representative point xi, yi inside the rectangle and using the value of the function at that point. So there's inaccuracies around how much the surface is, how much it deviates away from being exactly flat. If the surface was exactly flat at the top of the rectangle, then this would be exactly the volume of this bit lying underneath the surface. But if the surface is not flat, if it's sloped, then this volume here just approximates the volume between the surface and the xy plane. And there's also errors accounted for at the edge of R. Whether I'm missing out bits of R because my rectangles, don't capture bits of R, but there's a little bit of R left out, or maybe some of my rectangles creep over the boundary of R. So there's a bit of vagueness or inaccuracy accounted for there. But what we do is we take the limit of this process, the limit of this quantity, well, the limit is what? Well, the limit is the size of the rectangle, these small rectangles you're looking at, as the size of them approaches 0. Okay, so you're taking some finer and finer subdivision of your region R, so splitting it up into many, 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 many tiny rectangles Ri. So the size of these rectangles is approaching 0. You're taking the limit of that process. And then the inaccuracies dissolve away, so to speak. The inaccuracies around what's going on at the boundary of R converge to 0 because your rectangles are getting smaller and smaller, so they can better approximate the curved boundary of the rectangle. And the inaccuracies brought about by using just one representative point in the middle of the rectangle to represent the behavior of the surface above that rectangle, those inaccuracies converge to 0 as well because the size of the rectangle is decreasing and decreasing. So the representative point is only representing an ever-shrinking region around it. So in the limit, it'll give a perfect representation. So this is how we define the volume of the region. Volume of the region of R3, and how the integration, the double integral, is defined. So what we mean by this double integral of the function f of xy dx dy over R is the limit of this summation of the areas of Ri by f of xi yi as, well, let's say the radius of Ri approaches 0, or as the maximum radius of these rectangles approaches 0. Basically, as the rectangles get smaller and smaller. Sorry, the limiting, sorry, this is the, of the limiting process is the summation is happening over I. Okay, so that's a kind of a general sketch of the construction of these things. What we're seeing in section 1.4 here is an example of the simplest case. And this is where R, where the region R we're talking about is itself a rectangle. Okay, so not some region with a curvy boundary, but is itself a rectangle that is aligned with the coordinate axes. Okay, so it's the nicest kind of rectangle you can have. So here's our x-axis, our y-axis, and R we're considering is some rectangle. So there are limits a and b on the x-axis and limits c and d on the y-axis that completely describe that rectangle. And here's our z-axis, and we've got our surface lying above here. And we're talking about the volume of this part. Okay, there's a slightly better version of that diagram on page 28. So just to be sure, if we just draw the xy plane, the region R we're talking about is a rectangle that's aligned with the coordinate axis, as opposed to some rectangle which is rotated, which doesn't have sides parallel to the x and y axis. So this is the simplest kind of region to deal with. And in this case, we have an interesting way to think about these double integrals because there's two integral signs. And here we really see why there's two integral signs. Because this thing actually breaks down into a repeated integral. So what was up to now just a kind of maybe an undefined bunch of symbols, a double integral sign with a double differential dx dy. This thing down here we see is much more recognizable. We have an inner integral, which is just an integral with respect to one variable, dx. This will give us some particular value. Well, what will be the result of this integral? Well, you see, we'll be integrating out the x variable. The x variable goes from a to b. but there'll still be y's present in here. So this inner integral will be a function of y. But then it itself gets integrated with respect to y between the limits of c and d. This inner integral has an interpretation. This is the area of the curtain within the volume at location y. Now we'll try and draw a good picture of that. Here's our rectangular region R. Here's a typical location y along the edge of the rectangle between C and D. And lying over that horizontal line so this picture is taking place within this picture. I didn't try and squeeze it into that one, so it's a bit too small. Okay? So this picture you think of as like taking place within this one. So we're talking about at a specific location y. So this is somewhere along the y-axis between C and D. And at a particular position there, we've got what we can call a curtain, which is a two-dimensional area. Curtain is a two-dimensional area. It's lying over the line which is parallel to the x-axis at location y. It's got straight vertical sides, and its the upper side of it, the upper boundary, is determined by the shape of the surface. So this upper surface is defined by the function z equals f of xy. But the y coordinate is this particular y coordinate down here. So that's what this inner integral gives you. It gives you the area of this cross-section of the three-dimensional volume, the cylindrical volume here. We've taken a cross-section of it at the value y, and what we see is this two-dimensional cross-section, and it has a certain area. But what happens if you sum the areas of cross-sections? If I've got a volume, and I take cross-sections of it, and I examine the area of each cross-section, and I sum them all up, that gives you the volume. Okay? The volume you can think of as the sum of cross-sectional areas. Okay? So integrating these areas, integral of CD of the cross-sectional area at location y, integrating that with respect to y, summing up all these cross-sectional areas between C and D, this gives you the volume lying over R underneath the surface, as we talked about before. Okay, this gives you the volume of this cylindrical subvolume of R3 lying over the base rectangle and underneath the surface. But this method here, as its repeated integral representation, this is how we actually evaluate it. Okay? So we evaluate it or compute it using this representation. Okay. So let's look at an example. So example 1.18. So which rectangle are we talking about? We're talking about the rectangle between x0 and x2 and y1 and y3. So y equals 1, y equals 3, x equals 0, x equals 2. Okay, so we're talking about this rectangle here. So I want to do the double integral over R of f of x y dy, dx dy, where the function we're integrating is 2xy plus 4x plus 3y plus 1. Integrating over this rectangle here in the xy plane. Okay. Well, this becomes the repeated integral, where we integrate from y equals 1 up to 3, the integral from x equals 0 up to 2 of our function 2xy plus 4x plus 3y plus 1 with respect to x, and the inner integral with respect to y in the outer integral. So this is this representation that we had here. Okay? And this now looks, it's a repeated integral. And each integral is the kind of thing we recognize. But we have to do it in the multivariable sense. So just like when we were carrying out partial derivatives, you took a partial derivative of a function with respect to x, you temporarily treated the other variables, okay, just y if it was a function of two variables, you temporarily treated the other variable as if it were just a constant, and you did the differentiation with respect to x using the techniques you knew. Well, here is a similar thing, but with integration. So I want to integrate this two-variable function with respect to the x variable. So I temporarily assume that any y's I see are fixed constants. They kind of are, because this integral is going to be a two-dimensional area at a particular location y. So the y, as far as this integral here is concerned, the y is just some fixed quantity. And I'm integrating out the x variable using the standard rules and techniques of integration from x equals 0 to x equals 2. So the result of this inner integral, there won't be any x's left after I've done the integration. I'll have integrated them all out. But there will be y's left. That's expected. We expect this inner integral to be a function of y, just as we expect the area of this vertical curtain to depend on y. Because as you push this curtain backwards or bring it forwards across the rectangle, the top of it might be changing. Okay, because the top of it is moving across the surface. And depending on the complicated shape of the surface, this top part of the curtain might be changing shape. So we expect the area of it to depend on the location y. But we'll see that come out now. So the outer integration process remains unchanged. And inside, we integrate away with respect to x. So integrating 2xy with respect to x looks like x squared y. Integrating 4x with respect to x looks like 2x squared. Integrating 3y with respect to x, well, that looks like 3yx. And integrating the constant 1 with respect to x gives us x. But this is a definite integral with respect to x, so my integrated function needs to be evaluated at the limits x equals 2 and 0. Now, thankfully, there's a factor of x in each part, so when you put in x equals 0, you just get 0 all the way. So we just have to evaluate this at x equals 2. The y integration is just left there at the moment. So when x is 2, you get 4y plus 2 by 4 is 8. When x is 2, you get 6y. And when x is 2, you get 2. So as expected, the result of that inner integration is a function of y. 10y plus 10. Four and 6y, 8 and 2. So the value of the inner integral does indeed depend on the y value. It's equal to 10y plus 10. But then this is finally looks like something we can integrate. 5y squared plus 10y. All evaluated at 1 and 3 for y. So you'd have 45 plus 30 minus 5 plus 10. What's that? 75 minus 15? 60? So 60 units is the value, or is the measure of the volume lying above this rectangular region and bounded on the top by the surface, defined by that function z equals f of xy, but we're talking about this function of f of x and y here. Okay.
Measure of the volume of what?
Of the cylindrical type region. It's not a round cylinder. It's a cylinder with a rectangular cross section all the way up, except for perhaps its top surface. The top surface is provided by the surface defined by this function, z equals f of xy. So it's this volume that we were indicating here in this diagram here, or that's indicated here on page 28. The volume of this tower, this portion. Okay. Now that's the simplest kind of example. One where our rectangle is nicely aligned with the x and y variables, x and y axes.
Oh, no.
What we need to do is to make this a bit more sophisticated and wider, being applicable in all situations when faced with any region. So we've got we at least should be able to deal with regions which are not rectangles. We will still, in order to evaluate any of these, we'll still need a pretty concrete description of the region, not just like a wavy general one I might sketch on paper. But as long as we have some concrete systematic description of the base region R, we should be able to make a good stab at evaluating these integrals given a reasonable function f of xy. So that's what we'll be doing in the subsequent lectures. Okay, good luck. I'll see you for these lectures next week. In the meantime, we'll have tutorials. Good luck with the coursework. Please keep your work moving on the coursework.